Okay, folks, I've got 3 after. So yeah, we'll go ahead and get started. What we'll talk about today is correlation. And so I think in the syllabus, I had correlation coming before we were going to do ANOVA, but anyway, we're doing correlation now. There is a chapter that is in the SPSS book that talks about the procedures for correlation. There is also a PDF on Moodle that is very short. It talks about correlation. And so just read that when you have a moment. What we'll do today is we'll go over the PowerPoint. There is a website I'm going to show you that you can play around with the scatter plot. That it was very helpful in showing you how the R statistic is calculated based on a 2-dimensional scatter plot. And so the scatter plot is one of these very commonly seen statistical, fairly sophisticated, but fairly commonly used statistical graphs to show the strength and the direction of the relationship between 2 things. So we'll take a look at that. There's a website on there right above where it says exercises class, a correlation class exercises. There was a web link to this website where I'll show you that. The exam was posted, exam 2 was posted, so that is due on Friday. And so just make sure that you are on top of that. Of course, it's not due until midnight on Friday. So you will have time to come to Friday's optional session if you want to talk about the exam. And yeah, okay. So, but the exam does not have correlation on it. Exam just covered up to ANOVA. Correlation will not appear until the 3rd exam. Okay, so correlation is not on it, but the exam nevertheless is due on Friday. So okay, so let's go over this slideshow. I have a fairly brief slideshow talking about correlation. Okay. Okay, so you all should be able to see my slide show right now. Okay, so what you're seeing is this is a scatter plot. This is a scatter plot of 2 variables. On the bottom axis, or the x-axis, the horizontal axis, that is life expectancy in years. And then on the vertical axis, the y-axis, there is per capita health expenditures in US dollars. And our units of observation here are countries. They are countries. So this is the title of this graph: health expenditures and life expectancy in 30 OECD nations. And so you've got 30 observations here. The observations are countries, and it's showing you the correlation or the relation between per capita health care expenditures and life expectancy. And so while we know that correlation is not causation, it nonetheless is something. It does show us that there is a relationship here. And what we're seeing here is that it looks like as per capita healthcare expenditures increase as they go up, so does life expectancy, because we see the dots for countries down here at the low end with spending relatively little on healthcare, and then countries that spend a lot more, being further down here on the x-axis. So Switzerland, Iceland, Australia, compared down here to Poland, Hungary, Turkey. Okay, and so you have what's called a positive correlation here, because it looks like the scatter plots, the observations are going from the bottom left-hand corner to the upper right-hand corner. And so that makes the correlation positive. The other way of saying that is that people who live in countries where there is greater per capita healthcare expenditures tend to live longer on average than compared to people living in countries who have relatively low per capita healthcare expenditures. That's a positive correlation. Now, saying that, what that sentence I just said gives you the direction of the correlation, that it's positive as healthcare expenditures go up, so there's positive life expectancy. But it doesn't really tell you quite the strength of the relationship. Like, if you spend a little bit on healthcare, does life expectancy go up a lot? Or if you spend a lot, does it only go up a really little bit? So that is a question of strength, or a test of association. And this is the first time really that we're talking about a test of association in the class. Normally we've talked about tests of strength, or I'm sorry, tests of significance, but this is a test of strength, test of association. And so correlations tell you, they tell you a direction if something is negative or positively related. They also tell you if something has a strong, weak, moderate relationship, and then also if the scatter plot that you're seeing, if this is there just purely by random, or if this is there in some pattern that's beyond chance. And so there is the classic statistical significance test that goes along with this. So there's really three things: it's direction, strength, and significance that a correlation can tell you. And so to the degree that if we pretend that we have this imaginary line that starts down here where it says 68 and it goes all the way up here to the top, to the upper right hand corner. Now, if every single dot, every single country observation was sitting right on that imaginary diagonal that cut the graph in half perfectly, the correlation would be a perfect 1. It would be a perfect positive correlation. Because there is deviation from that imaginary line, the dots are deviating from that. That makes it less than a perfect positive correlation. And since we have a relatively small number of observations in this particular graph, we can look at the outliers, the deviance. And you notice the United States is quite deviant here in the sense that it's statistically not with the rest of the pack. We spend a lot more on our health care compared to other countries who we're similar to, but we don't get as much bang out of our buck. We're back here below 78 years on average. And this data is from a few years ago, but it's gone up maybe a little bit. Actually, I think life care in the life expectancy in the United States has gone back a little bit. So it may be about the same. So we'll say it's right here compared to countries like Switzerland, Iceland, Japan, way over here, spending considerably less than the United States but living a lot longer on average. And so they're an outlier in that sense. The United States is clearly the major outlier here, which makes this correlation less than a perfect positive correlation. It's a strong correlation, it looks like, but it's not a perfect positive correlation, because you have these dots on the scatter plot deviating away from this imaginary diagonal line, that if it were a perfect correlation, all the dots would line up on an imaginary line going up from the diagonal. So that's a positive correlation. So if we imagine a negative correlation, that would be something like we could have, rather than per capita healthcare expenditures, we could have number of cigarettes smoked daily, going from like 0 to 100. And what you would have there is the scatter plot going in reverse. All the dots would be clustered up here. They would cluster in this direction anyway, from the upper left-hand side to the lower right-hand side, showing that people that smoke the most tend to have shorter life expectancies than people that smoke the least. And so same thing though, we would have deviations from a diagonal running from the upper left hand to the lower right hand. It's not the case that for every cigarette smoked you live for sure so many fewer days. Some people don't seem to be as affected as much by smoking as other people. And so you're going to have deviations there, especially at the individual level, that'll make the correlation between life expectancy, the negative correlation between life expectancy and smoking cigarettes, less than a perfect negative one. It would be something short of a perfect negative correlation. Okay, and so you can have negative correlations, you can have positive correlations. You're talking about the relationship between two things, and they can be shown graphically on a scatter plot. So we'll play with that scatter plot on the website here in a second, but yeah, this is the example of a positive correlation with the two variables here being life expectancy and per capita healthcare expenditures, and with countries being the units of observation. So with correlations, just to get a little bit more into the details on this, you're talking about variables that have an amount that they're measuring. So you're talking about ordinal, interval, and ratio variables. You can't have a correlation like, let's say, between gender and race ethnicity. That doesn't make any sense. You do a chi-square in that case. You wouldn't look at a correlation. Correlation is looking at the relationship between variables that it would make sense to ask for an average for that variable. It would make sense to just ask the question, how much more of or less of do you have of this variable for this observation? So it's got to be those types of variables that you're using for correlation. It can't be nominal variables. And the directionality of the correlation here is important. So directionality is more important here than what we've talked about before. We've talked about before about how z-scores and t-tests can be negative, but that really wasn't of any major interpretive importance. But the direction for correlation really is important because they can be positive, meaning that, for example, like if poverty levels increase, so will the levels of violent crime. And so that's a hypothetical but easily demonstratable positive correlation that we see in social science data. A negative correlation of school funding decreases the rate of high school dropout will increase. So as one thing goes up, the other thing goes down. That is a negative correlation. And so we can see those as well. And then there's also correlations that don't follow a positive or negative trend. They're called nonlinear. And they can be confusing because they make it look like there might not be, at least at first approximation, any relationship between two variables. But in fact, there might be a very strong relationship. It just can't be modeled in a linear way where it's a graph, a scatter plot graph. So one example from criminology, we know very well that crime increases with age up until about 18 years of age, and then it declines. So it follows a rise and then fall pattern. your likelihood of being involved in criminal or any risky behavior does not just continue to increase over the course of your adulthood. It goes up pretty rapidly in adolescence and then declines, crashes, in fact, pretty quickly around age 22, 23 years old. People stop taking unnecessary risks, not nearly as much, at least when they're compared to when they're 15 or 16. So that can make it look like, if you just run a correlation between age and delinquency, or age and criminal offending just across a large number of observations with varying ages, it can make it look like there is no correlation between age and crime, but there really is. And age is one of the strongest predictors of it. So yeah, there's directionality, but we have to use common sense and theory when we're interpreting correlation coefficients, because it might be a non-linear relationship between two things, and the correlation won't be sensitive to that. So there is this aspect of strength, how strongly associated two things are. So correlation coefficients, what we call the Pearson R, so the statistic is R, is what like the letter R. And the R can range from -1 to +1. And so if it's negative, that means it's a negative correlation. If one thing goes up, the other thing goes down. If it's above 1, or if it's if it's above 0, then that means it's a positive correlation. If one thing goes up, the other thing will go up. And so here I just giving a few other examples here of correlations just to demonstrate strength. And so shoe size and height, yeah, those things are pretty strongly positively correlated. I'm just making up correlation coefficients at this point. R equals a 0.6. And so remember, you can't get any higher than a 1. You can't get any lower or any stronger on the negative side than a -1. So 0.6, you're 60% there of being a strong relationship as you can. But it's not a perfect one, meaning that not in every instance, if you find people with higher, taller or bigger feet, are they going to be taller than people with smaller feet? Not in every instance, but you could say 60% of the cases that's going to be true. And you can say that with correlation, but you don't want to do that too often, because it's not really a percent. But you can say in 60% of the cases that you find people who have big shoes, they're going to be taller on average than the people who have smaller shoes. But it's a strong positive correlation. Income and life expectancy. Now that one probably, again, a positive correlation, but maybe only of moderate strength. So R equals only a 0.3, because there's going to be some exceptions because of the things that maybe money can buy that cut your life short. But generally speaking, yeah, it is true that as income rises, so does life expectancy. That's generally true in the population, but there's enough exceptions to say that that may only be true for 30% of the total cases. So you have a strength there that's of only moderate strength, an R equal 0.30. IQ and delinquency, that's another one that we find consistently. It's consistently found that especially among boys that have learning disabilities, as measured by a low IQ, are also more likely to be involved in delinquency. But it's a weak correlation, meaning that it doesn't have that much predictive power. There's a lot of exceptions, or it may just not have that much influence over your risk taking. That is how your verbal IQ is measured. So it's on the negative side. That is the case that as IQ rises, the risk of delinquency does fall, but not by much. So as IQ rises, the risk of delinquency falls, but not by much. It's a negative correlation, but it's a weak negative correlation. And then there's other things that are probably no correlation whatsoever. R would be equal 0, number of pets owned, and frequency of marital infidelity, or whatever. You can correlate any two variables that are ordinal interval or ratio, but garbage in, garbage out, folks. Just because you find a correlation doesn't mean, just because you can correlate something doesn't mean it's going to come up with anything different from 0, or that's going to be meaningful at all. So, so correlations have the strength interpretation to them, and it ranges on the strong side of the negative. It's, -1 is the strongest negative, and +1 is the strongest positive. All right, and so here is the formula for finding correlation between two variables. So you have two columns of numbers, X and Y. You could plug this into, plug this into the computer and find this out. Or if you're really sadistic, more masochistic, I should say, you could do it by hand. But that anyway, that is looking at how one would calculate the relationship between X and Y, looking at the sum of them multiplied together and over the square of the sum differences. And so that's something that you could do by hand, but we won't do that. That's just what the equation looks like for calculating R. Here is something that you can do. I'll do this in class as a demonstration. And so this example, obviously Obama's in there, so a couple years ago. But a correlation here, how would you rate Obama's job performance, ranging from 1 to 5, poor to excellent? How would you rate the performance of the Republican Party? Ranging from a 1, poor to 5, excellent. And so, and here are the results that I just made up. And so we can look at the questions and we can probably guess that most likely this is going to be a negative correlation. People who thought that Obama did a good job are not going to be the same people who would rate the Republican Party highly, and vice versa. So it's going to be a negative correlation. And look, if you just look at the columns of numbers, you can kind of assess without even running a correlation that these two things are negatively correlated. So here, this person got a 5 here and they got a 1 here. This person got a 1, they got a 5. This is a 3 and 3. Here's a 3 and 3. Here's a 2. Here's a 4. Here's a 4. Here's a 2. Here's a 5. Here's a 1. Here's a 1. Here's a 5. Here's a 3. Here's a 3. Here's a 3. Here's a 3. So when the numbers are different from one column to the next, one tends to be high and the other tends to be low. So that's going to, right there, you can just eyeball it and see it's probably going to be a negative correlation, in addition to knowing something about the social world, political world, and realizing that, yeah, if you really ask people these questions, you would most likely get a negative correlation. So let me try to do this. I'm going to, oops, let me stop sharing for a second. I'm going to cut and paste, excuse me. I'm just cutting and pasting those values directly from SPSS. Oops, okay. I'm sorry, from the slideshow. And I am going to, let's see. Oops. You probably can't see that. Let me make sure. Just let me make sure. Okay, I'm just going to cut. I'm cutting and pasting that data that I have. Okay. So, so this is, we got to remember what this is asking. Obama job performance, good, bad, 1 to 5. Republican approval of the Republican Party. Same thing, scale 1 to 5. Okay, and so our question is, what is the nature of the relationship? What's the direction of the relationship between these two variables? We probably can surmise it's most likely negative. What is the strength of the relationship? Not sure. It looks like it's probably going to be pretty strong. So you can have a strong negative relationship. If one thing is high, the other thing is always going to be low consistently. That's going to be a strong negative relationship. And if those things are both true, it is almost certainly going to be a statistically significant relationship. That is, the pattern of data here in the two columns of numbers could not have been laid down by chance. So the fact that if they were laid down by chance, then the chance is diminishingly small, really small, like no greater than 1 in 20 chance, or p is 0.05. All right, so in order to run a correlation and find out all this information in SPSS, what you need to do is go to where it says analyze, and go to where it says correlate. Okay, so we have not gone here before, but this is a new entry under analyze, and go to correlate. And you go to where it says bivariate. It's the first entry. There's other ones there, but you want to go to where it says bivariate. Bivariate indicates that we're looking at the relation between two variables. Okay, and so these things are not labeled. We were just pretending Obama approval rating, Republican Party approval rating. And so we're taking them and putting them both over here to our analysis box. And the Pearson correlation coefficient is checked by default. That's what we want. That's the most common type of correlation coefficient. There's also by default the two-tail test is checked, and that's the one we want to test for, right? We're not assuming that the relation is going to be above, or I'm sorry. We're not assuming that the correlation is going to be negative or positive. We're just assuming that there is going to be some relationship. We're not specifying the direction. So therefore, it's a two-tail test. Two-tail test is the most common type of significance test that's done in statistics because it's considered to be the more conservative, safer test. All right, so go ahead and hit OK. Let me go ahead and stop sharing for a second, then go to the output. All right. Okay, so we should see right here, down here in this box, the very bottom. Hopefully people can see that. If people can't see that, somebody just yell at the screen, but it says correlations. It's looking at the correlation here between the first variable and the second variable. And what you see here in this first entry, you read across, it says Pearson correlation. And we look over here, how is a variable 1 correlated with variable 2? It is a -1, okay? So that means that in every instance in which one number was different from the other number in the adjacent column for the same case, it was always lower or higher. Okay, so that was true for every single one of those cases, those observations from the data that I just pulled from the PowerPoint. That's why it's a perfect -1. So you can't get any more negative than this. All right, so for every case, it's true. If you had anything better than a neutral rating on one item, you would be the opposite of that on the other item. And so I just set it up like that, so it would come out like a -1. Usually correlations, especially with individual data and large numbers of observations, are never as close to a -1 or a +1. But anyway, this is, you can see it's checked as negative, so it's a negative correlation. It's a 1, so it's a strong negative correlation. Okay, and so the second entry down here, it says SIG two-tailed, and so that means two-tailed significance test. And so your p-value here is 0.000. And so that means that, yeah, there's less than, well less than a 1 in 10,000 chance that you are observing the data that you're observing merely by chance, or that those numbers would be arranged like that merely by chance. Okay, so that's a significance test. So it is a negative correlation. It's a strong negative correlation, and it's statistically significant. Okay, and here's N. This is just the number of observations that were in the data set, 10 observations in the data set for two variables. So there's that. And then notice here that down here, the diagonal from this is the exact same information. This will always be the case unless you do something with the SPS output to suppress it. It will always come up as printed like this, so that you're seeing here the correlation between variable 1 and variable 2, and down here you're seeing the correlation here between variable 2 and variable 1. Okay, so it creates, it reprints the identical information on a diagonal directly opposite to it. And so you'll always see that, so don't let that confuse you. That is the exact same information. It's doing the same thing here when you're looking at the correlation between variable 1 and variable 1 and correlation between variable 2 and variable 2. Well, it's showing that as a perfect 1 as the correlation, which it always will, because a person's score on one variable will always be the same on the same variable. So that's it. It's just the way that the SPSS prints it out. You'll always find that there is a diagonal of 1s that are going down the correlation matrix. And this is what this thing is called. It's called a correlation matrix because you can put a bunch of items in there and see how they're all correlated together. But that 1 is there because, look, you're looking at the correlation between scores on variable 1 and scores on variable 1 for each individual case. So they're always going to be, it's always going to be a perfect 1 because the scores are always going to be the same on the same variable measured for the same person. So that's what that is. So you can kind of just know that if you're looking, all the stuff that's printed below the diagonal of 1s is just a repeat of everything that's going to be printed above the diagonal of 1. So there's going to be a diagonal of 1s that runs down a matrix, and everything that's printed above it is just repeated below it. And so you can choose to look at everything above the diagonal of 1s or choose to look at stuff below the diagonal of 1s, but you don't need to look at both. Okay, so that's a correlation matrix. Let me run that again. I think, can I request a scatter plot? Let me see. Can I do it through here? Maybe not. Maybe not. Wait. No. Okay. Well, they must have moved it. Well, anyway, that's the correlation correlation matrix. Let me show you a scatter plot. Let me show you the website. Okay. So can everybody see this? Everybody should now be looking at this scatter plot where it has a bunch of dots and you see a line, a diagonal going up between the dots. Can people see that? No? Okay, let me. Okay. Can we see it now? There is. Okay, great. It looks like people are shaking their heads. Yes. So, okay, this is on SPSS, or I'm sorry, this is on Moodle, the link to this. And so this is just something I want to show you here real quickly. You can play with this. Right now, this is looking at the relationship between generic variable X and generic variable Y. And it's showing you a correlation coefficient of a 0.244. And this is what it would look like visually. And if we would want to make that a correlation that's a stronger positive correlation, look at all these dots, how they're all spread out. You can move it, these observations, and see how the correlation coefficient now is going up. And you can play with this thing and see how it is the case that you can make it a stronger positive correlation to the degree that those dots are closer to this line. And so that line that you see there, that's the line of best fit. That's the line that's trying to minimize the distance between all these points. And so, yeah, I've got the correlation now up to a positive 0.719. And so it's also showing here with the Venn diagram what's called the shared variance. And so what that is showing is how much overlap is shared between one variable and the other variable. Okay, and so there's a direct relationship between that and Pearson's R correlation. But here, this is just giving you a sense of where the Pearson's R correlation is coming from in a visual aid here with the scatter plot. And so if you can flip this around and have all the dots going down like this way, and then there will be a negative correlation. But anyway, okay, that's that. So you can play around with that and get a better intuitive sense of just how correlations are represented with visual data. Let's take a look now at a couple of examples of correlations that I would like to do with SPSS. Let me find my screen here. Okay, let me try it now. Okay, so here are some exercises that we can work on in class that are looking at correlations and questions that you should be able to answer when you run the correlation. And so we've already done this with the example from the PowerPoint, but this is from AdHealth. These are variables from AdHealth. So there's that, and then there is also the assignment 8, and so that's due on Monday the 15th, and so you can take a look at that. So that's already posted on there. So anyway, this variable, past year attend religious service and general health, the relation between these two variables. So we should be able to answer the questions for all this. What is the correlation value? What is the direction of the correlation? What is the strength? What is the significance level? What does the significance level tell you? Provide an interpretation for the results. You may not use the words positive, negative, or significant in your interpretation. Okay, so for that last one, folks, for these, what I'd like you to do is try to be as non-statistically jargony as possible and say in plain English what the correlation between the two variables means in a way that your grandmother would understand it. So that's, you answer all the technical questions in the first few, and then the last one, you want to try to say, well, what is the relationship between these two things? What is a way I can say it in layman's terms, as they say? So don't use the words negative, positive, or significant. Like, people who attend religious services regularly are in better health on average than people who do not. That's what we'll find here when we look at that correlation, but that's what I mean by a non-jargony, layman's terms interpretation of a correlation between two things. So you shouldn't have to use any mathematical terms to describe it. You'll do that previously with answering those previous questions. All right, so yeah, if we take a look at, first what we want to do with these is look at these in variable view to make sure that we know how they are being measured. H1RE3 and general health. Okay, so let me oops, I did not want to do that. Okay. H1RE3. Okay, and this is the one. Yeah, past year attend religious services. And this is how this was measured. So this was asked of all the Ad Health respondents. Once a week to 4, never. Okay, so this is reverse coded, as they say. So the higher the score, the less frequent they are attending church services. So we just have to keep that in mind. Okay, and then the health one, I believe, is actually measured the same way. That is that it's reverse coded. So let me just double check on that. Health is H1, GH1. That's a question that we've looked at before in our exercises. It's the question, how is your health? And this is general health. And yes, it's the same problem, so to speak, of having one being the highest, being indicating the best health, and then 5 being the worst health. So in that case, we just have to keep in mind that these things are coded the way that they are, that high scores on both of them indicate low levels of that low levels of that thing being being measured. That is, high scores on health mean poor health, and high scores on attendance mean low attendance. But since they're going in the same direction, actually, and that makes our task of interpreting the correlation kind of simple, because it just means that they're both going in the same direction. So it doesn't really complicate our interpretation all that much. We just need to be aware of how things are measured before we enter into correlation mode. Okay, so let me stop sharing this for a moment and go back to, okay. So let's go ahead and look at this in a correlation. So we're going to analyze, going to correlate by variate, and we're going to go, I'm going to search variable names. I'm going to search alphabetically, and I'm going to go H1, GH1. And H1RA3, yeah. Okay, and we don't have to do anything else here. I'm gonna hit OK. And oops, let me stop sharing here and go to the okay. So here you should see the output, the correlation is here. We have a correlation of general health and attendance at religious services. It's a correlation of a positive 0.080. Okay. And so it can be interpreted as health improves, so does attendance at religious services, or as attendance at a religious services improves, so does general health. So it's positively correlated, meaning if you're high on one scale, you tend to be high on the other scale. If you're low on one scale, you tend to be low on the other. But there are a lot of exceptions to the rule. It's a correlation that is positive, but it's only 0.080. And so it is a weak positive correlation because it is definitely significant. See the significance test here, 0.000, p value is 0.000. So that means that there's a pattern here that definitely is not random. And the pattern shows that with greater attendance at religious services, the better self-reported health, but it's a weak positive correlation. And you can read into that in lots of different ways. What exactly that means, it could mean that attending church a lot just doesn't do much for your health, but does a little something, or it could be true for a very small proportion of the population, like 8% of the population, as the correlation coefficient suggests. So there's that. So it is a weak positive correlation. It's statistically significant. And oh yeah, and here this 5,609, that is the number of people who'd answered both items, who answered both questions, general health and past year attend religious services. Okay, and so that's another example of, and again, this whole thing is, because I use the word correlation matrix. This is the correlation matrix. This is what this thing is. Just that's what they call it. The correlation, the output for correlation is a correlation matrix. And yeah, so I think that's all we're going to do for today. We'll do a couple more examples on Wednesday, and people can talk about we can do the homework if you want, but that is it for today. You are free to go unless you have questions, you want to hang out for a little bit. That's great. But other than that, I'll see you all on Wednesday. Okay, take a look at that homework and be confident that you can do it. Okay.